हेलो स्टूडेंट्स, आज हम पढ़ेंगे चैप्टर नंबर 12 इलेक्ट्रिसिटी।
We use electricity for almost all the appliances at home. Lights, fans, the television, the music system, and the computer all run on electricity. Electricity drives our world. Electricity is also known as electric current. In this lesson, you will learn about electric current, its causes and applications. At the end of this lesson, you will be able to identify the features of electric current, explain how potential difference generates electric current, define electrical resistance, identify the factors affecting resistance, and state and apply Ohm's law. Before learning about the cause and applications of electric current, let us examine the features of electric current. Typically, in a conductor, free electrons move randomly. When these electrons are influenced to move uniformly in a specific direction, we get electricity or electric current. The direction of electric current is the same as the direction of flow of electrons. Electric current requires a continuous path of conductive material to provide a conduit for electrons to travel through. Electrons move in the empty spaces within and between the atoms of a conductor. As each electron moves uniformly through a conductor, it pushes the one ahead of it. Thus, all the electrons move together as a group. When you unplug an appliance, say a toaster, from the power supply, the flow of electrons is interrupted and the appliance stops working. You can measure electric current as the rate of flow of charge or the amount of charge flowing through a point per unit time. Electric current is measured using an ammeter. The standard metric unit for current is ampere. Ampere is often shortened to amp and is denoted by the unit symbol A. 1 ampere is equal to 1 coulomb of electric current per second. Electric current is a result of potential difference across 2 points in a conductor. Potential difference is the difference in number of negative charges that leads to flow of electrons. Electrons flow from negative potential, that is, the point with more electrons, to positive potential, that is, the point with less electrons. Whenever there is a potential difference, the current flows from the positive potential end to the negative potential end. Numerically, potential difference is the work done in moving a unit charge between 2 points in an electric field against the force of the electric field. Potential difference is measured using a voltmeter. Potential difference is often referred to as voltage and is represented by the letter V. If the work done to bring a charge of 1 coulomb from one point to another is 1 joule, then the potential difference between the points is 1 volt. As against potential difference, potential is the work done in bringing a unit charge from infinity to a point. Thus, if the work done to bring a unit charge from infinity to a point is 1 joule, then the potential at that point is 1 volt. In the given example, potential difference between points A and B is the difference in the work done in moving a unit charge from point A to B. Conductors can be in solid as well as liquid states. In solid conductors, positive ions are immobile and only the negatively charged electrons flow from high negative potential to positive potential. This flow of electrons is known as electric current. In liquid conductors, the current is caused by the flow of charged particles in both directions at the same time. In addition to potential difference, electric current is impacted by another factor called electric resistance. The electrons in a conductor do not travel in a straight path from one end to the other. While moving across the conductor, the electrons collide with fixed atoms within the conductor, encountering hindrance in their movement. This hindrance or opposition to the flow of electrons is called electric resistance. While the electric potential difference between two terminals encourages the movement of charge, resistance discourages it. Thus, the rate at which charge flows from terminal to terminal is the result of the combined effect of these two quantities. The standard metric unit of resistance is ohm, represented by the Greek letter omega. When 1 ampere current flows through a conductor across a potential difference of 1 volt, its resistance is 1 ohm. Resistance to charge flow within a conductor is affected by some clearly identifiable variables. First, the resistance of a conductor is directly proportional to its length. The longer the conductor, the more resistance it offers. After all, if resistance occurs as a result of collisions between electrons and the atoms of the conductor, then there are likely to be more collisions in a longer conductor. More collisions mean more resistance. This relationship between resistance and the length of the conductor is termed as the law of length. Secondly, the resistance of a conductor is inversely proportional to its cross-sectional area. Larger the area of the conductor, lesser the resistance offered. This relationship between resistance and the area of a conductor is termed as the law of area. The third factor that affects resistance to charge flow is the material that a wire is made of. Some materials are better conductors than others and offer less resistance to the flow of charge. For example, silver is the best conductor. However, silver is never used in wires of household circuits as it is expensive. Copper and aluminium are among the least expensive materials with suitable conducting ability to permit their use in wires of household circuits. The conducting ability of a material is often indicated by its resistivity. Resistivity of a material is the resistance offered by a conductor having unit length and unit area of cross-section. The resistivity of a material depends upon its electronic structure and its temperature. The fourth factor that impacts the resistance of a conductor is temperature. For most materials, resistivity increases with increasing temperature. The variables affecting resistance can be mathematically written as R is equal to rho L divided by A, where R is the resistance in ohm, rho is the resistivity in ohm meter, L is the length of the conductor in meter, and A is the cross-sectional area of the conductor in meter square. In 1827, a German scientist, George Simon Ohm, conducted a series of experiments to study the variations in electric current when the potential difference across a conductor was changed. With the findings of his experiments, he postulated Ohm's law, which explains the relationship between electric current, voltage, and resistance. Ohm's law states that electric current through a metal conductor in a circuit is directly proportional to the potential difference or voltage across it, and inversely proportional to the resistance between its ends. Thus, according to Ohm's law, voltage V is equal to the product of electric current I passing through the conductor and the resistance R offered by it. Let us use an example to see how these equations help us analyze simple circuits. In the given circuit, there is only one source of voltage, a battery with 12-volt EMF, and only one element of resistance to current, a lamp with a resistance of 3 ohm. Using Ohm's law, you get the voltage in the wire as 4 ampere. In this lesson, you will learn about the types of electric circuits and examine how a closed electric circuit works. At the end of this lesson, you will be able to illustrate the working of an electric circuit, identify the significance of circuit diagram, define the types of electric circuits, calculate the equivalent resistance in series circuits, and calculate the equivalent resistance in parallel circuits. The electric current in a circuit is due to potential difference between two terminals of the battery. To illustrate the concept of potential difference and the nature of an electric circuit, consider two metal plates positioned parallel to each other. Each of these plates carries an opposite charge, one positive and the other negative. This arrangement of charge plates creates an electric field in the region between the plates. This field is directed away from the positive plate and towards the negative plate. A negative charge from the negatively charged plate moves towards the positive plate. This occurs without the need of energy in the form of work. It occurs naturally and thus lowers the potential energy of the charge. In the given arrangement, the positive plate is at higher potential and the negative plate is at lower potential. Thus, there is a difference in electric potential between the two locations. Now let's connect these plates using a metal wire. On connecting these plates, the wire serves as a sort of pipe for the flow of charge. Gradually, negative charges move from the negative plate through the charge pipe to the positive plate. As a negative charge leaves the lower plate, the plate becomes less negatively charged. Similarly, as a negative charge reaches the positive plate, the plate becomes less positively charged. The amount of positive and negative charge on the two plates slowly diminishes. Eventually, the electric field between the plates becomes so small that there is no observable motion of charge between the two plates. The plates ultimately lose their charge and reach the same electric potential. In the absence of an electric potential difference, there will be no charge flow. This illustration demonstrates the working of an electric circuit. For a true circuit, charge must flow continuously through a complete loop, returning to its original position and cycling through again. The necessity for a complete loop in a circuit can be demonstrated through an example. If you take a battery pack, that is, a collection of cells, a light bulb and some connecting wires, and make a circuit, the bulb lights up. However, when you disconnect the wires, the bulb does not light up. The fact that the bulb lights up and remains lit when the wires are connected is evidence that charge is flowing through the bulb's filament and that an electric current has been established. A closed loop through which charge can continuously move is referred to as a closed circuit. If the loop is not complete, then charge stops flowing, and such a circuit is known as an open circuit. Also, for continuous flow of charge, there should be an electric potential difference across the two ends of the circuit. This potential difference is usually maintained by the use of a cell or a battery. Constructing an electric circuit can be a complex task, as a circuit uses various kinds of electrical components. A diagram is drawn to represent the components and flow in a schematic form. This schematic representation of various electrical components using suitable symbols is called a circuit diagram. Circuits that consist of just one battery and one load resistance are very simple to analyze, but they are usually not found in practical applications. Most often, you find circuits with more than two components. You can connect the components in a circuit in two ways: in series and in parallel. Let us first examine a series circuit. In a series circuit, each device is connected such that there is only one pathway through which current can traverse the external circuit. Each charge traversing the loop of the external circuit passes through each resistor consecutively. In a parallel circuit, each resistor is placed in its own separate branch. The presence of branch lines provides multiple pathways for a current to traverse the external circuit. On arriving at the branching location or node, a charge selects the branch on which it will travel back to the low potential terminal. Thus, each charge passing through the loop of the external circuit passes through a single branch. Consider the series circuit shown in the figure. Since there is only one pathway through the circuit, every charge encounters the resistance of every device. Therefore, adding more devices results in a larger overall or net resistance. This increased resistance serves to reduce the rate at which charge flows. That is, it serves to reduce the electric current. The rate at which charge flows through the external circuit is the same all through. The amount of current varies inversely with the amount of overall resistance. There is a clear relationship between the resistance of the individual resistors and the overall resistance of the circuit. As far as the battery supplying the charge is concerned, the presence of three resistors R1, R2 and R3 in series is equivalent to having a single resistance equal to R1 plus R2 plus R3 in the circuit. The equivalent resistance of a circuit is the amount of resistance that a single resistor would need in order to equal the overall effect of the collection of resistors in the circuit. For series circuits, the mathematical formula for computing the equivalent resistance R equivalent is equal to R1 plus R2 plus R3. The current in a series circuit is equal at all points. Charge does not pile up and begin to accumulate at any given location. Therefore, the current at one location is never more than that at other locations. Similarly, charge is not used by resistors. Therefore, the current at one location is never less than that at other locations. Thus, charges can be thought of as marching together through the wires of an electric circuit, all at the same rate. The amount of current flowing through the circuit is the same at all points. The current in the first resistor is equal to the current in the last resistor and the current in the battery. That is, the total current passing through a circuit is equal to the current at any point in the circuit. Mathematically, you can write I total is equal to I1 is equal to I2 is equal to I3. You can calculate the current if the battery voltage and the resistance of individual resistors are known. Using the individual resistor values and the equation above, you can compute the equivalent resistance. Additionally, using Ohm's law, the current in the battery and thus through every resistor can be determined by finding the ratio of the battery voltage and the equivalent resistance. That is, I battery is equal to I1 is equal to I2 is equal to I3 is equal to V battery divided by R equivalent. In a series circuit, the battery supplies energy to the charge to move it through the cells and to establish an electric potential difference across the two ends of the external circuit. As the charge moves through the external circuit, it encounters a loss of electric potential. This loss in electric potential is referred to as voltage drop. If an electric circuit powered by a battery V is equipped with more than one resistor in series, then the cumulative loss of electric potential is V volts. Thus, there is a voltage drop for each resistor, but the sum of these voltage drops is V volts. The same as the voltage rating of the battery. The total voltage drop of the circuit can be expressed mathematically as V is equal to V1 plus V2 plus V3, where each voltage drop is equal to the product of the total current in the circuit and the resistance in the respective resistor. Substituting the values of individual voltage drops in this expression, you get IR is equal to IR1 plus IR2 plus IR3. By solving this expression, you get the equivalent resistance of cells in series circuits, R, as the sum of resistances of each resistor in the circuit. Hence, R is equal to R1 plus R2 plus R3. In a parallel circuit, there are multiple pathways by which current can flow. If you add another resistor in a separate branch, it provides another pathway for the charge to flow. Therefore, when more resistors are added to a parallel circuit, the overall resistance decreases. This decreased resistance increases the current. This phenomenon can be explained using the example of tollways. A toll booth provides resistance to car flow on a tollway. Adding more toll booths in a toll station will provide more pathways for cars to drive through. These additional toll booths will decrease the overall resistance to car flow and increase the rate at which they go through. Similarly, in a parallel circuit, charges divide up into separate branches. Based on the resistor in each branch, the current across branches can vary. Nonetheless, when taken as a whole, the total amount of current in all the branches is equal to the amount of current at locations outside the branches. Thus, the amount of current in the circuit is the same across all points outside the branches. However, it is split over multiple pathways. This principle can be represented as I total is equal to I1 plus I2 plus I3, where I total is the total amount of current outside the branches and in the battery, and I1, I2 and I3 represent the current in the individual branches in the circuit. In a parallel circuit, a charge does not pass through every resistor. Rather, it passes through a single resistor. Thus, the entire voltage drop across that resistor must match the battery voltage. It doesn't matter whether a charge passes through resistor 1, resistor 2 or resistor 3. The voltage drop across that resistor must equal the voltage of the battery. Put in equation form, this principle is expressed as V is equal to V1 is equal to V2 is equal to V3. Let the equivalent resistance be R. As you saw earlier in series circuits, you can calculate the amount of current flowing through each resistor as the ratio of the voltage drop across that resistor to the resistance of that resistor. Substituting the values of I1, I2 and I3 in I total is equal to I1 plus I2 plus I3, you get V divided by R is equal to V divided by R1 plus V divided by R2 plus V divided by R3. This gives you 1 divided by R is equal to 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. Electric appliances convert electricity into heat energy, providing you energy in a form that you can use. In this lesson, you will learn how electrical energy transforms into heat energy. At the end of this lesson, you will be able to describe the heating effect of electricity, identify the cause of the heating effect of electricity, illustrate the working of an electric fuse, state and derive Joule's law. When you switch on a bulb, the thin metallic wire or filament in the bulb turns red and the bulb starts glowing. This is because when an electric current passes through a metallic conductor, the conductor gets heated. Thus, electrical energy is transformed into heat energy. This is called the heating effect of electricity. Many appliances in our household utilize the heating effect of electricity. Some common examples are electric irons, room heaters, and storage water heaters. How does the electrical energy of current get converted into heat energy? Every conductor offers resistance to the flow of current. When a potential difference is applied across the ends of a conductor, the free electrons in the conductor start drifting from the low potential end to the high potential end. These electrons collide with the positive ions. That is, the atoms that have lost their electrons. When the collisions take place, the energy of the electrons is transferred to the positive ions, making the ions vibrate more violently. This creates resistance to the flow of electrons. The electric current has to overcome this resistance. The work done by electric current in overcoming this resistance is converted into heat energy. This is the heat that you use in your electrical appliances. Metallic conductors used in electrical heating appliances to convert electrical energy into heat are called heating elements. For example, the filament in a bulb is a heating element. A good heating element should have high resistivity so that it gets heated quickly, high melting point to enable it to withstand high temperature, negligible variation in resistance due to temperature changes. Three metal alloys most commonly used as heating elements are nichrome, an alloy composed of 80% nickel and 20% chromium; manganese, which is 86% copper, 12% manganese and 2% nickel; constantan, a copper-nickel alloy with 60% copper and 40% nickel. If your electrical appliances receive very weak or very strong current, they could be damaged and stop functioning. To prevent such damage from fluctuations in the current, an electric fuse is used in the circuits of most houses these days. An electric fuse is a safety device used to protect an electric circuit against excessive current. The mechanism of the electric fuse is based on the heating effect of electricity. You may have often heard people talking about replacing the fuse in their homes because the fuse blew, cutting off the power supply. An electric fuse contains a fuse wire that is designed to withstand a particular amount of electricity flowing through it. When the electric supply fluctuates and the current becomes too strong for the wire, it melts and breaks the supply of electricity. Electric fuses are rated according to the current that they can withstand. For example, a fuse rated 5 ampere can withstand current flow to the maximum of 5 ampere. If the current flowing through that circuit exceeds 5 ampere, the fuse wire melts from the heat, cutting off the power supply through that circuit. We can monitor and control the heat generated by electric current by regulating the current supplied to an appliance. James Prescott Joule, a British physicist, expressed the relationship between the heat generated in a conductor and the amount of current flowing through it. This relationship is popularly known as Joule's law or Joule effect. Joule's law states that the amount of heat produced in a conductor is equal to the product of the amount of current squared, the resistance of the conductor, the time for which the current passes through the conductor. To derive Joule's law, let a potential difference of V volts drive a charge Q coulomb through a heating element, and W be the work done. The potential difference is a measure of work done in moving a unit charge across a circuit. From this, we get equation 1. V is equal to W divided by Q, or W is equal to VQ. The amount of electric current passing through a circuit is the product of the rate of electric current and the time of flow. From this, we get equation 2. I is equal to Q divided by T, or Q is equal to IT. Substituting the value of Q in equation 1, we get equation 3. W is equal to VIT. Now let's use Ohm's law. V is equal to IR. In expression 3, to get the formula for the total work done by electric current. The total work done by electric current, W, is equal to I square RT. This work done by electric current to overcome the resistance of a conductor is converted into heat energy, which is represented by H. Hence, H is equal to I square RT. You have learned in earlier classes that power is the rate of work done, as energy is the capacity to do work. Energy and work are equivalent. Hence, we also define power as the rate of consumption of energy. In terms of electricity, the rate of consumption of electricity is electric power. When an electric current flows through a conductor, the rate of consumption of electricity by an electric circuit is also the rate of dissipation of electrical energy in the form of heat through the conductor. We have seen earlier that electrical energy is expressed as W is equal to VIT, or W is equal to I square RT. Hence, electric power can be expressed as P is equal to VIT by T. This implies P is equal to VI, or P equals to I square RT by T. This implies P is equal to I square R. Substituting V by R for I in the expression P is equal to I square R and simplifying, we get electric power equals V square by R. The SI unit of electric power is watt and is denoted by W. 1 watt is the power consumed by a conductor having a potential difference of 1 volt across its ends when the current passing through it is 1 ampere. As watt is a small unit, for commercial purposes, we use a bigger unit, kilowatt. A kilowatt is equal to 1000 watts. According to the definition of power, energy can be represented as the product of power and time. For commercial purposes, the unit of electric energy is kilowatt-hour, denoted by kWh. Simplifying the expression, 1 kilowatt-hour is equal to 3.6 into 10 power 6 watt-seconds. As 1 joule equals 1 watt-second. 1 kilowatt-hour equals 3.6 into 10 power 6 joule.
आज हमने समझा चैप्टर नंबर 12 इलेक्ट्रिसिटी। नेक्स्ट क्लास में हम इसी चैप्टर को कंटिन्यू करते हुए इस चैप्टर में आने वाले न्यूमेरिकल पार्ट को समझेंगे। थैंक यू।